everyone. Welcome to our session. We will be giving an intro and deep dive of the Kubernetes SIG Storage. My name is Xing. I work at VMware by Broadcom.
I'm Hemant. I work for Red Hat on OCP Core Storage.
Hi, I'm Michelle. I work at Google.
Here's today's agenda. We will talk about what is SIG Storage, what we did in 1.30 and 1.31 release, what we're working on in 1.32, and finally, how to get involved. In SIG Storage, Saad and myself are co-chairs, Michelle and Yang are tech leads. Other than the leads, we also have many other contributors. We have more than 6,000 members on the SIG Storage Slack channel, and we have about 30 unique approvers for SIG-owned packages. What we do in SIG Storage is defined in our charter. SIG Storage is a special interest group that focuses on how to provide storage to containers running in Kubernetes. The terminologies that you heard most in SIG Storage are probably persistent volume claims, persistent volumes, and storage classes. Persistent volume is the type of storage that lives beyond a pod's lifecycle that allows us to support running databases in Kubernetes. PVC is in the user namespace. It represents a user's request for storage. A PV is in the cluster scope. It represents a resource on the storage system. A PVC and a PV have a one-to-one mapping to each other. A storage class defines the classes of storage that is defined by the admin. Different storage classes can map to different quality of service levels or other policies defined by the admin. In dynamic provisioning, storage class can be used to decide what type of provisioning to use and what parameters to pass to the provisioner to create a volume. We also support ephemeral volumes, and ephemeral volume becomes available when the pod becomes available and then goes away when the pod goes down. Local ephemeral storage, such as empty-dir, can be used as a scratch space for the pod. We also have secrets that can be used to store sensitive information. We have config maps that can be used to inject config data into the pods. We have CSI ephemeral volumes that require a special CSI driver, such as the secret store CSI driver. And we have generic ephemeral volumes that allow any plugin that supports dynamic provisioning to be used as an ephemeral volume and have its lifecycle bound to a pod. And in 1.31 release, there is a new volume type called image that allows a container image file or artifacts to be mounted into the pod. Kubernetes volume plugins include in-tree plugins and auto-tree CSI drivers. Most CSI drivers, most in-tree plugins are already deprecated or migrated to CSI drivers. We still have some in-tree drivers. We have NFS, iSCSI, FC volume plugins. They can be pre-populated with data, and it can be used by the pod. We also have local volume, representing a mounted local storage device that can be used by a pod. Container storage interface CSI that defines the common interfaces for a storage vendor to write a driver and have its underlying storage to be consumed by the containers running in Kubernetes. And CSI is the recommended way to write plugins. So that's a quick intro. Now let me hand it over to Michelle, who will talk about what we did in 1.30 release.
Okay, thank you. All right. Yeah, so in 1.30, we promoted a couple of features to GA. First, we redesigned the way that volume reconstruction works. If you're unfamiliar with what volume reconstruction is, it's a feature that is needed to support kubelet restarting. When kubelet restarts, we lose all of the in-memory state we have about what volumes are mounted and to what pods. We have to reconstruct that state by scanning all of the mount points and volume metadata that we keep in the node's file system. And so we completely redesigned this feature to fix a number of bugs and make it more reliable. So in the 1.30 timeframe, I think you'll find that scenarios where a kubelet restarts or crashes, we'll be able to recover from that more gracefully. Another feature that we GA'd was to control who can change the volume mode when restoring from a volume snapshot. So while most workloads interface at the file system level, backup software commonly has optimizations for backing up data at the block level. So to do this in a Kubernetes environment, the backup software has to be able to create a temporary block PVC from a file system volume snapshot. So we want to allow backup software to be able to do this kind of operation, but we want to prevent most other users from being able to do this because there were previous security vulnerabilities in the file system layer, and so we want to protect users from being able to exploit that. And so this feature makes it possible so that, or it basically requires that somebody with administrator privileges has to opt in to allow these snapshots to basically have their mode converted when we restore. And so this is a potential behavior change. If any of your applications used to rely on this kind of workflow, you now have to opt in at the administrator level to be able to allow this behavior. But otherwise, if you're doing a typical snapshot restore flow where your snapshot is taken from a file system and you're just restoring it to a file system PVC, then you're fine, and there's nothing you need to do there. Also in 1.30, we introduced a new alpha feature to improve performance for SC Linux relabeling. So this is relevant if you're using an operating system with SC Linux enabled. I think that's mostly Red Hat distributions, but I believe other Linux distributions also support it as well. Before this feature, we would recursively walk through every file in a volume to properly set the SC Linux label on it. And so if your volume has a lot of files in it, this could take a really long time. It could take hours, potentially, if you have a very big volume. So now with this feature, we'll use a Linux mount option called context, which applies this mapping a lot faster. In order to use it, there's a couple of criteria that needs to be met. First, the CSI driver needs to declare that it supports mounting with this context mount option. In addition, the workload needs to provision the PVC using the read-write once pod access mode. This allows us to turn it on by default because we know the read-write once pod mode is safe and won't break workloads. But if you do want to enable it for any volume, you have to explicitly turn on this SE Linux mount feature gate. But it does have the potential to break workloads that share volumes. And so this should be done in a test or staging environment first. We're also adding additional documentation to detail all of the steps and how you can detect if your workload is compatible and how to resolve it if it's not. So if you're using an environment with SE Linux, be on the lookout for this. Moving on to 131, one of the main features that we promoted to beta is the ability to modify existing volumes. So this is to support use cases like tuning performance parameters on PVCs after they're created. How it works is we've added a new object called volume attributes class. It's similar in concept to a storage class. However, the biggest difference is that storage class is only used for dynamic provisioning, whereas you can actually change the volume attributes class after a PVC has been created. And so there's a new field in the PVC object now called volume attributes class name. You can change it after it's been created, and the CSI driver will actually go and change the underlying volume to the new class. To walk through an example here. Here we have two volume attributes classes, one called silver, one called gold. So silver, you can specify your IOPS to 5,000, and gold will set it to 10,000. The PVC is initially provisioned with silver, but after some time, you realize that you need to allocate more performance to this workload. So then what you just do is you modify your existing PVC object and change the volume attributes class to gold. And that will signal to the CSI driver to go ahead and actually change the underlying storage volume to allocate 10K IOPS to it. So this feature has to be supported by the CSI driver you're using. If this is interesting to you, please check your CSI driver's documentation for more details on how to use the feature and exactly what parameters your CSI driver supports. Another feature we promoted to beta is to support the PV reclaim policy regardless of the object deletion ordering. So in the past, you've always had to delete the PVC object first, and then allow the driver to then clean up the PV object. If you did it in reverse and you deleted the PV object first, then it would not actually trigger deletion of the underlying storage system. And so this feature basically adds a finalizer. So if you delete the PV object first, we will actually wait and wait for the PV object to be deleted and go through the proper deletion flow so that everything will get cleaned up properly. And lastly, we promoted to GA a feature to add a last phase transition timestamp to the PV object. Whenever the PV changes a phase, such as when it goes from available to bound or bound to released, then we'll also record the timestamp of when that transition occurred. So this is mainly useful for metrics and also observability of the persistent volumes. So yeah, now I'll hand it over to Hemant to talk about our more recent features.
I'm going to cover what we did in 132 and what we're working towards in next releases. So one of the features that we are working in 132 is change block tracking. And what that allows is a vendor-agnostic backup and snapshotting service via change block tracking. The idea is a driver advertises this capability, which would expose the gRPC service that will allow tracking of blocks that had changed, and it allows incremental backups and other services. So as part of this feature, we are releasing a sidecar called Snapshot Metadata Sidecar, which will expose a TLS gRPC service on which the backup vendor is supposed to listen and get the change blocks, and this way you can do the incremental backups basically. And we have been working on container object storage interface for a while now. It's still in alpha, and then we have been working on volume health. It's a feature in the CSI driver that can expose like whether it is working normal, abnormal. So it's currently exposed as matrix. So we want to evaluate, get feedback, and see how to make this feature more useful for users. So one of the other features that we are moving to beta in 132 is recover from resize failures. So if you have used volume expansion, you might have seen that if you expand the size to too big of a value I don't know, accidentally, or the storage provider doesn't have enough size available, it just gets stuck. There's no way to recover from that. There's a manual process, but it's pretty lengthy. So having this feature will allow you to reduce the volume size and retry volume expansion. And it also exposes the resize status at a more granular level. You can see the status of PVC, in which state the resize operation is. And because of these extra states that are available to us, it fixes many long-standing bugs and risk conditions which were previously hard to fix. So it should be more robust in 132. And as Michelle said, we have been continuously working on improving SLNX relabeling, which is time-consuming. It was done by container runtime. It used to time out. It was pretty expensive. So it's default in 131 for read-write once pods, but we are working to make it default for all volume types. And what we are doing is we have introduced this new feature gate called SLNX change policy, because by default, when we enable this feature for all volume types, there's a potential to introduce some breaking changes. So having this additional feature gate, which allows you to configure this SLNX change policy in your pod, allows you to opt out of using mount option for SLNX relabeling. So that could improve your performance of pod startup and whatnot. Another thing we are doing is that because it has potential of breaking your pod, we want to emit matrix and we want to emit events when there's a potential that, okay, two pods are using same volume but with conflicting SLNX labels, then we want to inform both the pod authors that, okay, your pod may have errors. So that's something we are introducing in 132. By the way, just a show of hands, how many of you are using SLNX on your OpenShift, or sorry, Kubernetes clusters? Okay, so yeah, if you have any questions about it, please talk to me, Jan, or us after the talk. So this is a brief table of like what could potentially break. I don't want to get into too much detail of it, but essentially, like if there's a potential that your pod will be broken once the SLNX mount feature becomes default, then you should get matrix, you should get alerts, and it will be documented to help you guide through this process. And yeah, sorry. And obviously, if you don't want to use this feature, you can, again, opt out of this by setting the SLNX change policy to recursive so that it goes back to previous behavior. This feature, the new SLNX as a mount feature, also opens up use cases that were not possible before, which is read-write many. As you can see, you can now mount same volume on two different nodes with two different SLNX contexts, and both pods will work, which was previously not possible at all. So it unlocks some new features that will be interesting. And another feature that we have been working in 132 is moving volume group snapshot to beta. And this is mostly out-of-tree feature, and it introduces these three new API types: volume group snapshot content, volume snapshot class. And it allows you to specify a selector and take the snapshot of all the volumes that match the selectors together and know when they're ready to use and consume and use the snapshot. So if you're interested in this feature, please talk to Xing and or on Slack. So, and yeah, one more feature we are moving to GA in 132 is when you scale down stateful set. Currently, the PVCs that was created for this, the pod, backing pod is left, or delete the stateful cell. So PVCs are left. So this new feature, persistent volume claim retention policy, allows you to configure the behavior of what happens to PVCs when you scale down the stateful set, what happens to the PVC when you delete the stateful set, whether they're retained or whether they are deleted. So this could be useful for folks using stateful set. Some of the features that we have been working towards, which are in various stages of design and prototyping, that we are quite not shipping in 132. is one of them is the supporting volume expansion through stateful set. So currently, if you're using stateful set, the only way to expand the volume is expand each PVC individually, which could be tedious, actually. You might have to take down the workloads. It depends. So there has been a consistent demand to allow users to expand all the persistent volumes that are in use by stateful set by directly editing the stateful set stateful set template. So it's a difficult feature, but we have been working on designing this. Hopefully in 133 we'll have alpha version of it. Another feature that we have been working on is like combining various sidecars like attacher, resizer, provisioner into a single sidecar. It's tedious to maintain all these different sidecars, bump them, fix CVEs, and all sort of things. And then merging them into one process will also allow us to reduce CPU and memory footprint of all these sidecars, because they can use the shared informer and whatnot. And one more feature we have a proposed design in 132 which couldn't quite make it, is the making CSI node allocatable property mutable. If you use volumes, you know that on AWS, GCE, or other cloud providers, there's a limit of how many numbers volumes you can attach to a node. So CSI node allocatable property has a count that each node tells the scheduler how many volumes could be attached to this node. And based on that, scheduler decides whether to schedule a pod on that node or not. But on many cloud providers, the value can change based on ENIs attached to the node, or GPUs sometimes attached to the node. So we are making the allocatable property of a CSI node mutable and making sure that scheduler can see the change and dynamically adjust the limit as it changes. So this will allow the system to be more accurate. Less pods will be stuck in container creating state. And yeah. One more thing we are working on is the storage capacity scoring, which allows you to score the nodes based on available capacity. So that could be useful for folks. And as you know, we have been doing entry to CSI migration. At this stage, I believe like most cloud provider-based drivers have been migrated to CSI. We are hoping that we'll migrate Portworx driver from entry to CSI in 133. As all storage vendors and our users are using CSI more and more, we are seeing less use of entry drivers. So we are in process of deprecating and removing the entry storage drivers we used to ship. So this is the list of drivers that we have removed from entry. And one of the drivers that has been deprecated, not yet removed, is Git repo driver. We are hoping it will be removed in Q4 of 2025. And I spoke with folks, and they're interested in getting involved in and helping us. That'll be great for Kubernetes community, for storage community. So we have the SIG storage page here, and we have a bi-weekly meeting every Thursday at 9 a.m. Pacific time, and then we have issue trials meeting where we discuss all the whatever issue that has been raised in Kubernetes against storage at 10 a.m. Pacific time every Wednesday. Then we have some sub-project meeting for container object storage, CSI, data protection. We have a mailing list that you can join. We have 3 different Slack channels that you can join where you can ask us questions that you might have. And these are the resource page which you can use for getting more information or reading documentation. That's all we had. Thank you.